In this video, we'll do a quick review of electricity so we can use these electrical principles in our design lab. We'll start by reviewing some terms, and we'll start with the term voltage, which is the electric potential. It's a potential for charge to move. It's from potential energy. It's potential energy per unit charge. It's measured in the unit volts, a capital non-italicized V, named after volta, so we use a capital letter. It's potential energy. Just like with potential energies, only potential energy differences can be measured, so only voltage difference can be measured. And we use the variable, if we're trying to represent a voltage, we use a variable V also, but that's an italicized font. If we look at this diagram here, if we want to represent voltages in this diagram, we would look at positions within the diagram. Potential energy is an energy of position, so position is important when we're looking at voltage. So if we look at the voltage difference between these 2 points in this diagram, we could measure that and we'd have a potential difference. One's positive side, one's negative side, and let's just call this Vx. If we wanted to measure another potential difference in the diagram for measuring from this, if this is position A and this is position B, we'll let this be position C, then we could maybe label this as VCB, where we use some subscript to help differentiate the different voltage variables. So we've talked about the term voltage. A battery is a device that can maintain a potential difference or a voltage across its terminals. That way it can then do some work to move a charge. So if we have a battery, we could connect it to this diagram here, and we've created what we'll call later, we'll define later, as a circuit. So we're able to maintain this voltage across the terminal. It will then do work to move the charge. So that doing work to move the charge, current is our next term, and that's the movement of net charge. It's a scalar quantity. It has a direction, however, but that direction does not make it a vector. It just tells us the direction of positive charge flow. That's important, but because we know within a wire, it's electrons within a conductor that move. They move in the opposite direction of the current. So our current is the direction of positive charge flow. It's measured in the unit of amperes. We use a capital A because it's named after our scientist Ampere, French scientist, and it uses a symbol I for the current variable. So if we look in this circuit here, we might have multiple currents within this circuit. This battery then is doing work to move a charge. We'll label the current flow. It's doing the work, comes out of its positive voltage terminal, and it moves the charge that we're calling this current, and we'll label it I subscript B. Resistance is our next term that we'll review. That's a wire or any other object's opposition to the current flow. It's measured in a unit of ohms. We use the Greek symbol omega for that, and it uses the symbol R for the resistance variable. We also denote, if we a resistor within a circuit, we have a circuit symbol for that. Our circuit symbol for a battery is shown here. Our circuit symbol for a resistor is shown here, and it looks like friction. So our Ohm's law then is our formula that can be applied to these electrical quantities, and it's true relationship that really defines resistance, and that formula is V is equal to IR. If a material is ohmic, which includes wires are ohmic over a range of temperatures, well, an ohmic material means that that resistance will not change as the voltage across it changes. So if we go back here, if we allow this symbol here to be a resistor, or R1, let's say we have a current then, I1 flowing through the resistor. We'll have a voltage across it, V1, and our V1 will equal I1, R1, and that's our application of Ohm's law. So these first 4 terms that we've reviewed are basic to electricity, to resistive or direct current electricity, which is what we'll be using this semester in digital logic design. An analogy to water can be done with DC circuits pretty well. A water pump trying to move water uphill is required because we know water will flow downhill due to gravity, but it won't flow uphill without some other work done. So a water pump moves water from a low pressure to high pressure, like a battery moves charge from a low voltage to high voltage. They're doing work. Once that pump has done the work, that force then will allow it to move through a closed pipe. It will flow by itself downhill, but as that pipe becomes smaller, the diameter becomes smaller, the friction within that pipe increases and will have a higher resistance to the flow of water. That's similar to the electrical resistance in a wire. So if our wire has more resistivity or is a type of material or an object, all objects have some resistive component to them. We can represent them in our circuit symbol here. So that's our analogy between water and electricity. The difference, of course, is that we could have a pipe that is void of water. We could have an empty pipe. We never have a wire that's void of electrons. Electrons are part of the material that builds up the wire. So within a wire, our analogy is that we always have our pipe starts out to be full. It's primed. We've already primed the pump. This hyperphysics link will show you is a good example of this analogy. So let's look at further concepts here, current concepts. So if we need a circuit, what does it mean to be a circuit? That's a closed path for current to flow. Water, if we, for example, let's go back to our previous diagram, if we break this pipe here, and it's no longer connected down here, but we still have this pump flowing, well, all this water will just flow out. That's not true of a wire. If we break this wire, it becomes open, and once it becomes open, current will no longer flow. So we need a closed loop in order for current to flow at all, in order for this battery to do work. It'll maintain a potential difference, but it won't have to do work unless we have this closed loop. And current, when it flows in the direction of voltage decrease. When we're going through the battery, our current's flowing in the direction of voltage increase because the battery is doing the work, but within the rest of our circuit, our current flows in the direction of voltage decrease. So when we say our V is equal to IR, it's important to use what we call passive sign convention. Our current is flowing in the direction of voltage decrease. Ground is another important concept. Ground is our 0 volt reference. We use this symbol. It's our earth ground, but we will use it in this class for all grounds. We also have circuit grounds and chassis grounds, different symbols for that. So when we talk about voltage, it's the difference between 2 points in a circuit, but we can also refer to what we call a nodal voltage. That's where the reference point is, other reference point is always ground. So this circuit only has a battery and a resistor in it, but we could take this node up here and we could label this VB, and we could say that VB is equal to whatever the voltage is of this battery, V battery. And we don't need to, we know that that's just at this node that's relative to this ground voltage here. That will become important for us because it's easier to measure things if we always have one of our voltmeter terminals at the ground. Then we can go through and just measure with one probe. So we'll be measuring nodal voltages in lab. Boundary conditions for resistance, well, the resistance can be 0, it can't be negative, so it can be 0, or it could be infinite. So short circuit is what we use to refer to 0 resistance. If there's 0 resistance, then the voltage across it is 0. An ideal wire is a short circuit. In a circuit diagram, wires are drawn, they are considered short circuits, no voltage drop across them. An open circuit is infinite resistance, so no current can flow through an open circuit. So this is also, if we think of a switch, sometimes we want to switch things into a circuit. If it's open, we have infinite resistance, open circuit. When we close it, it becomes like a wire, we have zero resistance, and we have that short circuit. So let's look at our current law. One of the current laws is given the option, more current is going to flow, it's going to follow the path of least resistance. So the smaller R, Ohm's law in terms of I is equal to V over R, the smaller the resistance, the higher the current if there's the same voltage across it. So here we have three resistors wired. They look like they're in parallel, but we have these three switches up here. The switches are all open. So because there's an open circuit, no current will flow. No current will flow through R1, through R2, through R3, but additionally, no current is going to flow from the battery. This battery will do no work. It will still maintain its potential difference across its terminals, but this current flowing is going to be equal to zero. The current cannot flow off into a bucket like water can. So that's our open circuit. When the switch is open, no current will flow. Our ground reference, we have, if we put our ground reference down here, then we can measure potential differences. The potential difference of this node, our nodal voltage, will be VB. It'll be the same as the battery relative to ground. But here, if we look at this V1 is going to be equal to 0. So V1 will equal 0, our V2 will equal 0, and our V3 over here, these nodes, we label those nodes, they'll all be equal to 0. So that nodal voltage, the voltage in reference to ground, V1 will equal V2 will equal V0 when all of the will equal V3, which all equals 0. When these switches are open, we don't have a closed loop, we don't have a circuit, but we can measure potential difference. We close the switch. If we just close the switch to connect resistor 1, then current will flow. We'll have IB flowing. It'll flow down through resistor 1, but this current will still be 0, so it won't divide, and IB will have to equal I1. The same current will flow through the resistor as flows through the battery. When we close all three switches, now we have these three resistors in parallel. They're in parallel. They have the same potential difference across them. We know that to be true because they have the same position at the top as at the bottom, because remember, these wires are short circuits. There's no voltage drop across them, so we say they're separated by the same 2 points, so they're all in parallel. They're all in parallel, they have the same voltage across them, so we can define their currents based on Ohm's law. So the difference in their currents is just going to be the resistance, but it's inversely proportional to the resistance. So since R1 is greater than R2 is greater than R3, then I1 will be less than I2 will be less than I3. If we were to add another switch into this circuit, but this switch didn't have any resistance associated with it. It just has a wire, and we close this switch. When this switch becomes closed, then I1, I2, and I3 are all going to equal 0. All the current IB is going to flow through this short circuit. And this is what we don't want to do in lab by mistakenly shorting something out. This will cause also our current, since the resistance is 0, that IB is going to approach infinity, or it's going to do things like burn things out, get things to melt. So Kirchhoff's current law is important to understand here. What flows into a node must also flow out of a node. So we say I in is equal to I out, or the sum of all the current into a node must equal 0. The current charge will not build up anywhere. That's from conservation of charge. So here we have IB flowing in, I1 plus I2 plus I3 flowing out. Well, we know these I1 and I2 and I3 based on the voltage of the battery, because that's the parallel voltage across the three resistors. So we can say that's equal to VB divided by whatever this equivalent resistance is that the battery is seeing? Well, we can define that equivalent resistance. 1 over that equivalent resistance is then 1 over R1 plus 1 over R2 plus 1 over R3, so we can find our parallel equivalent resistance. The power is also important. Our electrical power, that's the rate that energy is supplied or absorbed, which is always the voltage across times the current through an object. So in this circuit again, our battery supplying power, it's supplying power at or energy at the rate of the voltage of the battery times the current of the battery. And that must be equal to the power absorbed, because we must have conservation of energy, which means we must have conservation of the rate that energy is used, or conservation of power in this closed system, our closed circuit. So that's equal to our absorbed power, the voltage across resistor 1 times the current through resistor 1, plus that through resistor 2 and resistor 3. So that's our conservation of power equation for this circuit. Since we want the same voltage across each of our loads, that's how we wire our loads. We wire them in parallel. In digital logic, we want 5 volts across our loads for our integrated circuits. So that 5 volts, we're going to want to wire all our loads in parallel. What that means is that power supplied by the battery is going to be the sum of all these powers. And that's going to require the battery to drive more power. If they were all wired in series, then the equivalent resistance would be R1 plus R2 plus R3. So the current would be smaller, and we'd have less power absorbed in each of the loads and less power driven by the battery or supplied by the battery. So as we add more loads, that requires our power supply to deliver more power. So that's something we need to be very conscious of in lab. So we didn't do much with series equivalent resistance. That's a little bit easier to understand. If we did wire these 3 resistors in series, Kirchhoff's voltage law, the sum of all the voltages around a closed loop must equal 0. So as we increase in voltage across the battery, we're going to have our current flowing in this case clockwise. So our V1, we have a voltage drop in the direction of the current V2. And our V3. So we're going to have our Kirchhoff's voltage law gives us this equation, substituting and using Ohm's law. V1 is IR1, so our equivalent resistance is the sum of the 3 resistors. So let's just look at then a protoboard. If we take a look at a protoboard, this is what we'll use in lab. What we want to know is where are the short circuits and where are the open circuits. The reason for this protoboard is to help us wire our circuits together without us having to use solder. The difference between what's through the parallel red and blue stripes, here our short circuits are vertical. In between, our short circuits are horizontal. So if I first label the short circuits, these are short circuit all the way down, right? That's a short circuit, and I'll do this in orange. That's a short circuit. Between them are open circuits. Similarly, in here we have this 5 short circuits, and then underneath it 5 short circuits. It's hard to draw. I'm doing those on top of each other, so that's not quite right to show that way. We'll try to show that that's a short, and underneath it, it's open. So we have an open circuit between these 2 horizontal rows, an open circuit between these 2 vertical rows. And we have on the other side of our protoboard, again, these are short circuit vertically. That's a short circuit. And that's a short circuit. We don't have to do anything to wire it together. They're already wired together underneath the protoboard. This is a short circuit. We do it with this pen. There's a short circuit, and there's a short circuit. Between them, it's open. So let's just take a look. If we wanted to wire this circuit together, how we could do it on this proto board is we could use this node here and this node here, and that's how we could wire resistor 1. Plugging into here, now the top of resistor 1 and resistor 2 are connected. How are they connected? They're connected through the proto board, and the top of resistor 3 is connected. The bottom of resistor 1 and resistor 2 are connected. The bottom of resistor 2 and resistor 3 are connected. So we have these 3 resistors wired in parallel. This resistance, we're going to connect it to the top of the resistors, and then we're going to pull it over here. But we want to take this, this is shifted a little bit, we want to take this and take it over to power, and we want to take our ground wire and connect that as well. So we can take a wire as a short circuit and can tie that right in there. And between power and ground, that's where we'll put our battery right there. So we will practice this in lab with our proto board. We have a more sophisticated proto board that also has some power on it. It has some frequency generators on it. It has some LEDs on it. That's all for this review of electricity.